Perfect. So today we're going to talk about Newton's laws of motion. We're going to have like these summaries, these like rules that a lot of things follow. We're going to talk a lot about reaction forces, and look at a lot of examples today, so practice problems. And I think that's going to help you guys. I'm going to post a homework later today that'll be due Sunday, Monday, um, and kind of keep going. So right here, so this is kind of like the big picture, like what's the goal of Newton's laws, and then what are they? So Newton's laws of motion summarize properties of motion and how motion changes for an object for a wide variety of materials at speeds much slower than the speed of light. So we're not talking about relativity. We're not talking about like light itself. We're not talking about really fast moving particles at like the subatomic levels. So these laws, though, they're exceptionally effective for describing motion and changes in motion for dense, rigid objects, and they're pretty good for some fluids, for a lot of them, but not all of them. And that's what they are summarizing, right? So we observe things, we create ideas, we test those ideas with experiments, and then we fine tune them, and then we kind of do stuff with them, right? We use them in engineering, we use them in construction, we use them in medicine. So Newton's laws do not accurately describe properties of motion for extremely small objects. So we're not talking about quantum mechanics. We're not talking about like atoms or subatomic particles, even though at times these laws can work fairly well. Uh, Usually with materials, they still work, but not necessarily single atoms. We're not talking about non-Newtonian fluids like oobleck, that stuff that gets super rigid when it starts moving. And we're not talking about extremely large objects like in astronomy. So Newton's laws work for some planets in our solar system, and they work for some objects in space, but they don't work for all of them. But they're a really good approximation nonetheless. So that's why we keep teaching it, and they're extremely good when you're talking about solids and working with materials. Okay, so that's kind of why, and then these are the laws themselves. So I've kind of edited the way they're written in books a little bit. So the first law of motion is often called the law of inertia. It says the motion of an object will not change unless there's another object that acts on it and causes that motion to change. So another way this is said is an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. So that's the two ways to say the first law. The second law quantifies, so it's the mathematical version of the first law, because and it says the acceleration is directly proportional to the sum of interactions, the sum of forces, and it's inversely proportional, so you divide by the mass of the object. So a lot of times this is written as F equals ma, as a really simplified version, but it's really like the acceleration equals the sum of forces divided by the mass of the object. And then those all of these forces are about having a certain frame of reference where you're not accelerating as the observer. So there's a little bit of like when you start moving around yourself and start observing things, there's some extra things you have to keep aware of. But we're not talking about that today. The third law is that a force represents an interaction between two objects. So there will always be equal and opposite force pairs when drawing two force diagrams for interacting objects. So another way that is said commonly is for every action, there's an equal and opposite reaction. Now, that makes it sound like there's a first and a second, but with forces, they interact. It's mutual. It's at the same time for the force. And then we have to analyze the accelerations or the lack of accelerations that come from that. So those are Newton's three laws of motion. Today we're going to look at several things for all three. And you'll get these notes, so just give yourself space if you feel like I'm going a little too fast, or if you just ask me a question. So this is 3 alternative ways to say the laws, and then there's the ways they're said in the book. Okay, so let's explore this concept of inertia. So we like to say mass is a quantification of something's inertia. Mass is also a description of how much stuff you're made out of. And so I have a few videos. I'm going to go ahead and open them on a separate slide. So let me go ahead and share a different screen. Go ahead and share sound. Okay, so everyone should be able to see a balloon. There's a needle that's about to pop the balloon. And so real quick, what is acting on the balloon and the water inside? So there's something holding the balloons. There's some sort of pull up. There's all of the Earth's gravity pulling down, the weight. And then the balloon itself holds the water. So inertia is that your tendency to keep your motion. So right now the balloon is still, the water is still. And when we pop it, we see the balloon quickly move because there's a lot of tension in the balloon. And the water stays still. And this happens so quickly that we don't always notice this effect. So that's why we have, right? We like slow-mo. So kind of play that one more time. There's a lot of tension in the balloon material itself. And so when it's released, we see that balloon move quickly, but the water maintains that shape and then starts to fall. So that is the property of inertia. There's no weight that's really causing that. It's not the intermolecular forces of the water. Those help. But the fact that like this happens with solids as well as liquids is the property of inertia. So the next video I want us to watch thinking about this is what happens if you have a slinky. Let's go ahead and find a good spot. So right with a slinky, if you hold the top, the bottom will fall down and you can make it wobble back and forth. But then if you focus on its inertia versus its force, the force acting on it. So right around here, the 38 mark. So there's 2 different spring keys, just like show it. There's a hand holding it. There's the earth gravity pulling it, and then there's internal forces amongst the coils because they're connected. And so there's some tension in the spring, you might say. And so what property? Is it inertia or is it a force that causes what you see?
I'm going to drop them at the same time. You should see this stay pretty still and this just collapse.
So what property keeps the bottom part still? Because this happens quickly in real life, but we're going to slow it down. Is it inertia or is it force?
Onto the top of that before it falls. 3, 2, 1, drop. Cool. I forgot I had to trigger the camera. Do you know anything about the slinky, Dan?
Okay, they're about to say nonsense. So there's a force between the 2 ends, let's say. So the top part has the earth pulling down and the rest of the slinky pulling it down. And the bottom part has the earth pulling down and the rest of the slinky pulling up. So there's balanced forces for like the bottom part, but not for the top part. And then they fall together. So there are forces involved with the slinky. But the fact that the whole thing, right, like has a tendency to stay there, and then there's a force involved that actually makes it fall.
Do you know anything about the slinky, Dan?
Okay, and then this is an oldie but a goodie. This guy's name is Paul Hewitt. He's definitely like a little bit older. This is from like the 80s, where they would like tape classes. So here we have two strings or two rubber bands. There's a ball in the middle. So the ball has mass, has inertia, and then the earth pulls on it. That's what makes its weight happen because there's an interaction. And the goal here is he's going to pull it fast and slow. So we'll see what happens with each pull. He's going to ask them to make predictions. I just want you to see what happens. So
I'm going to say the top because I got another string here for the next.
okay, so let's go back a little bit.
Harder until either this string or this string's going to break. Which one do you think will break?
He's going to pull down slow.
I'm pulling that down. Don't I exert a tension in the string? Doesn't the string get tight? Huh? Twang, huh? Doesn't this one get tight too? And so I have a tension here. I also have a tension here. The string is stretched out. So as I pull gradually, which one's going to break, gang? Top or bottom? I'm going to say the top because I got another string here for the next trial. Let's watch this. It was the top. Because of the weight of the ball or because of the inertia of the ball? Check your neighbor and see if your neighbor sees which of the two.
So what he's pointing out is that the top string has the weight of the ball and the tension. So like I don't know how much they talk. But now, right, so you have two forces causing this tension up here, the pull and the weight. So the string breaks when you pull slowly. And then this time he's going to pull fast.
Quick, boom, it breaks. But how about now I take this string and I whip it down quickly like that. Why did the bottom string?
So now he whips it fast and the bottom string breaks. And it's because there's no time for any of that effect to translate up to the top string, and that's due to the inertia of the ball. So you can protect things sometimes with the inertia of something else.
Your neighbor. Okay, that's the last.
So then he does it with rubber bands.
How much that thing's stretching? Okay, but let's suppose I just go like this. Pull. With this elastic. If I pull, I can pull. Look how much that thing's stretching. Okay, but let's suppose I just go like this. Notice that? There was not as much force up here. The elastic didn't stretch as much when I pulled quickly. That force was not transmitted up here.
Wasn't transmitted. He calls the ball lazy. There's some other analogies for the inertia, but the idea is that things have a tendency to maintain their current states. And we call that property, that fact of our reality, inertia. Okay, so that's a lot about the first law. Are we talking about forces exerted, or are we talking about the inertia? Okay, so let me go back. Oh, I was gonna share one more slow-mo video, but we can do it later. Okay, here we go. Perfect. Okay, so in this case, with a slow pull, there's a long stretch. So longer stretch, more force on top rubber band. So that's the pull. And when he does a fast pull, we don't see much stretch at all. We see a break. So how much reaction time there is for how much time there is for things to happen. Some of those properties are inertial properties. So that's kind of the first thing I want to point out from those videos. That's what's going on in these other videos too. You have to say what part is the forces involved in the scenario, the interactions, what part is the inertia of the objects. Okay, what questions do we have before we go on to the example to go over how to use Newton's second law? Make sure I don't rush too much at all. Right, so I just got asked again. Let's go over that again. The slinky, I'm going to try adding a little page in here. The slinky, 1 second. The slinky has both. So with the slinky, when you're, so there's the top of the slinky and the bottom. The whole slinky, the whole object stays in place. Right, so the whole object stays in place. But then what we see is we see the bottom stays in place as well. Versus the top. So there's two things there. There's that so the top has two forces. It has the earth on top, and it has the coil, the rest of the coil on the top part. So that's unbalanced forces. And then for the bottom piece, we have the earth on the bottom, we have the coil on the bottom. But the whole object stays in place during that collapse, and then it falls. And so if you look at both of those together, the top and the bottom together, it looks like it should just fall from the earth pulling on it. And so that delay in the whole slinky falling is an inertial property of the slinky. So just want to make sure, someone asked for me to clarify that, so I want to make sure I did. So the whole object staying in place is the inertial property. So this is the inertial property of the slinky. And then the fact that the top is the one that falls down and the bottom stays in place, that's because there's balanced forces on the bottom part compared to the top coil. So that's why we see internally, we see one side fall, and then the whole thing falls together after that. So that's what I really want to point out with this Linky. So I'm glad someone asked. Perfect. Okay, so let's now. Why did that go to the next page? One second, I don't know why this. There we go. Okay, cool. Now let's look at an example for the second law. So the second law, mathematically, so we have the acceleration is caused by there being a sum of forces, and then the inertia, the mass of the object, reduces how intense that effect is. So sometimes we write it like this. We write it most of the time as sum of forces equals ma. There's a how many things are acting, what are their directions, what acceleration or lack of acceleration do we see. So here, standard xy coordinates are this. But it makes more sense to use these coordinates. And so they're called parallel and perpendicular right here. They're also called like normal is the word for it. This little n would be normal. And they're also called T or S. So T stands for tangential, or S can be surface. So I've seen S or T. I don't like to use T because we like to use time for T. So I'm going to use S for the surface. So it's normal to the surface, which is the perpendicular to the surface, parallel to the surface. I like to use it as an S coordinates personally, because perpendicular and parallel both start with P. Okay, so that's a different coordinate system to use. And then right here, this picture breaks down, there's a normal force from, this is the normal part of the reaction of the slope. And then there's a friction part of the reaction from the actual ground. Weight always pulls straight down. And it turns out if you have 25 degrees as the angle here, and I can show this whoever wants to later, it turns out that angle goes right here from geometry. So there's a really clear geometry reason, and I'm more than happy to show that later for why this is 25 degrees. So we're going to need to use cosine. So this is weight cosine of the angle. And then this is going to be weight sine of the angle. Okay, so let's first start with the free body diagram. So let's do the force diagram. So if we have a person, we know that the earth is going to pull down. I like to call it FG. What can the ground do? Well, the ground is going to react a certain way. So maybe the ground is going to have, some total amount of force. And so maybe the ground's total amount of force is something like this. This is the reaction from the ground on the skier. So this is the ground. We don't like to use G because we already use little g, so let's just say surface on skis. And then we break that down. We go, left and right are okay. So we say, okay, let's break this guy down into components. And so we'll have a normal force. It's got to cancel out this part. And then we're going to have a friction force. So this is called F normal. Or some people write little, like they'll write that. And then this arrow right here, I'm going to erase this stuff real fast. This is the friction. So those are two components. And then this is the angle and the slope. So it turns out usually the friction part's not that big. It might be more like this, size-wise. Okay, so that's the force diagram we have. And so we would say, we draw the force diagram, and then you could say sum of forces equals ma. And the acceleration is in the parallel direction, or the surface direction, going along the surface. Okay, so let me back up. So then we can say, okay, we know this part and this part have to be equal. Things I just put 2 dashes on. Okay, so that's what's going on. Look, see how I haven't said what everything is equal to. I've just been like, there's a diagram. I know there's an acceleration. Okay, but what's the question? So for this question, it's one of the examples. So there's a skier, and her mass, including her equipment, is 60 kilograms. So the skis, the poles, right, the clothes, person. What is her acceleration if friction is negligible, meaning it's 0? And what is her acceleration if friction is 45 newtons, constant? Like let's say 2 different stretches of snow, right? 2 different angles maybe, but same angle, let's say, but 2 different, like completely different patches of snow and ice on the hillside. Okay, well, we've done half the work for figuring out what's going on with this diagram. So let's go ahead and break that down. So if I go with these coordinates, I like to call them N and S. So sum of forces. There is an acceleration. That's what my equation says. And her acceleration is completely in the S direction. So this little symbol here with the S hat, that means in the S direction. So what I get to say is, okay, so sum of forces, there's the normal force, they're calling it big N. That's fine, I just don't prefer it. So and then there's the weight, and they're calling it in the perpendicular direction. That's in the normal direction. And then there's the weight in the parallel direction, and it's negative, plus the friction. That's in the S hat direction. So for part A, you can say F equals 0. That's what you're told. Okay, so I get to say, I can say Fn minus weight perpendicular equals 0. And so this comes from the fact that there's only acceleration in one of the directions that I picked for my coordinate system. So that's fine. And then I know that MA is going to be negative, the negative direction for the parallel weight. So that matches up. And weight is always going to be mg, and then the parallel side is sine 25 in this case, and g is always the same number. So it turns out the mass divides away. And I could say the normal force has got to be mg cosine theta. And so if I bust out a calculator, sine 25, put my calculator. There we go. Okay, so sine 25 is going to be close to 1/2. It's close to sine of 30. It's 9.81. This is going to be 4.1, say 5 meters per second squared. That's what I was asked for. And then I'm practicing solving for something else. So I wasn't told to solve for the normal force, but that is something you could be asked for. So I'm going to practice it real fast. So 60 times 9.81 times cosine 25 is about 533.4 newtons. Okay, so that's how you solve this sort of question. Okay, so I can always use this if we're on Earth. It's a given in red for G. This equation is me figuring out what's going on. Okay, there is an acceleration. It's totally in one direction if I pick this coordinate system. If I pick regular x, y, okay, I gotta break up things into more trig functions. So your acceleration will have 2 components, or you can say it has 1 component, and my forces, my net forces have 2 components. Yeah, so you gotta break down things into components. This coordinate system uses the least number of trig functions. Okay, what if f isn't 0? Because here, I don't have to know a whole lot about f. I just, oh, it's 0, perfect. Okay, so let's redo that. Okay, I can say the same thing. I can literally start from the same spot. Okay, it's Fn minus weight perpendicular in hat. And then I have friction minus weight parallel s hat, and that equals ma s hat. Okay, so I still have the same thing. I have Fn equals that perpendicular component, so it's still mg cosine theta. So it's still what I had before. Okay, perfect. Okay, what about this purple stuff? So now I have F minus weight perpendicular. Then I'm saying let's say they're still going to accelerate down. So I know the acceleration is negative. So I should write that. Like I'm saying it's going to be negative. I'm saying that component of the weight along the ramp direction is bigger than the friction. And I know that because I'm told they're skiing down the hill. And they're speeding up. I'm assuming they're speeding up. But I think you're told that in the question. But okay. So my goal is still acceleration. So ma equals weight minus the friction part. Okay, so I have this equation. What do I need to know? I need to know something about friction. Okay, it turns out this is kinetic friction. So I should have written a little K on all of it. Kinetic friction is equal to, it turns out, it's equal to what's called a coefficient of friction. So I actually don't need to know this yet, but something you do need to know in general is that it's some coefficient number times the normal force. In general. But in this case, I don't need to know that because I'm told. Okay, so it's mg, the parallel part is sine theta minus this kinetic friction over the mass. This is 4 different questions. Okay, so I have 60 kilograms times 9.81 newtons per kilogram, sine of 25 minus 45 newtons divided by 60 kilograms. Okay, so hopefully you're all feeling like it's coming together. Okay, I gotta put all those numbers together. So right, I set up the equation. I have like the facts, the ideas, the method. Okay, I get to the algebra. Okay, I gotta do some algebra. This equation doesn't come from nowhere. I have a very clear analysis process. Okay, so that is 203.7 for 60.0. So this is newtons, this is kilograms. Newtons over kilograms equal meters per second squared. 2 units are good. It's a little sanity check or sense making check. I get 3. Let's say 40. So that's the answer. Oh. Let's say that's the answer. Okay, let's do some sense making. How does that compare the acceleration we got before? Okay, so with no friction, so you can think of that as always like the maximum acceleration for a situation. So when you don't have friction, you're almost always going to have like a maximum or a minimum sort of value. More often than not, no friction means a maximum value. No air resistance means a maximum value typically. Every now and then it doesn't, but for the most part, that's what it means. Is this acceleration when there is friction smaller than when there's no friction? So 3.4 meters per second squared compared to 4.15 meters per second squared. Okay, I don't think I have any typos just based on like comparing them. I'm pretty sure like I did it right. That's like how I sense make in the middle of a test or a quiz or a homework problem. Okay, so the units are good. I'm gonna need to know this fact about friction later on for kinetic friction. So kinetic means you're moving. Static means you're not moving for friction. Okay, and I'm gonna upload all this later, so you're gonna have all the steps. But let's just quickly summarize them again. So you draw a force diagram, or you're given one. I'm just redrawing part of it over here. You kind of label what's going on in the problem. If you don't have a diagram, do a quick sketch, especially like of a ramp. I'm going to tell myself with equations based on my coordinate system. So once I have a coordinate system, then I get pluses and minuses. I use the angles. In this case, I might just give you this triangle factoid each time. But like this angle becomes that angle. Ask me if you want me to go over why that is. So I have pluses and minuses based on the coordinate system. And then I know they're accelerating down the ramp. They're not falling into the ramp. They're not sinking. They're not floating off the ramp. So the normal direction forces, or these perpendicular directions, have to be balanced. Add up to 0, which is this right here. And then I'm given this for part A, that the friction is 0. So I just let it go away. It's gone. Just what I did over here. So put a little plus 0. And then I break down the problem with algebra. Same thing over here. What am I given? Okay, from the same diagram, there's just the extra frictional piece that doesn't go away. I know they're accelerating in the negative direction, so I need to clarify that this time. Which I like here, I'm not clarifying it. So this doesn't have a minus sign because I'm trying to like think about it. But it really should have a minus sign, which is where these go away. Okay. Then I use my diagram to figure out, okay, cosine is the one next to the angle, sine is the one far away. So the what's called parallel, or in the S direction, gets sine theta. And what's perpendicular, or in the Y direction, or what is now the new Y, the N, gets cosine. And I have all the numbers, so I plug and shut. Okay, so the surface reacts, and it has these two components. So friction and normal forces are a reaction of the surface once something else is acting on it. So that's not a third law pair with the weight. So this wasn't a Newton's third law. This is a Newton's second law. I want to be really clear with that. I said, what's happening? Where is there an acceleration or not? Or which components, which directions is that acceleration happening? And then I say balanced or unbalanced components. From Newton's second law, I get this middle part, and then from doing the algebra and solving, I get the rest. I did not use Newton's third law in this at all. Okay, and then a follow-up question. So this is a follow-up using kinematics. So let's say she's already moving, so you would need to be given so need initial velocity of some kind to get the final. Otherwise, can only get delta V. So what I want to just point out is like you have to be given an initial velocity if they're already moving, which is what was told. So it's like, oh, not enough information to be to answer this question. So I need more information. But I can get delta V is this 3.4 meters per second squared number times 5 seconds. I just want to make it clear, like sometimes you have to be given more information to solve. Okay, and then let's do this question. I think it'll help with Newton's third law. So there's a horizontal floor. There's some sort of crate. Oh. And then on top of that crate, there's a person. Smiley face. So we know M of the person, M of the crate. And it says determine the magnitude of the normal force. That's our goal. The floor exerts on the crate and the crate exerts on the person. So in this case, I'm gonna draw the person in orange actually. So they're still smiling. There's the crate, which should be purple. There's the floor, which I think I drew in blue. And then there's actually the earth too. So in Newton's third law, the third law, you're going to have equal and opposite pairs. The interactions, you have to draw all of the objects that are all interacting. So these are each of our individual systems, if you will, whether it's one big system, and these are all the mini systems. So let's go ahead and make sure we draw the diagrams. So for forces, start with the person. Person standing on the crate. And they're not moving. So let me make sure I draw these balanced. So this is the earth on person. And this one upwards is the crate on the person. That's one of the normal forces we care about. Crate on person. Yeah, crate on the person. For the crate, there's the earth on the crate. And then there's the person on the crate. Let's draw these a little different sized. There's two forces. There's the earth on crate, and there's the person on crate. And then there's got to be, adding up to both of those, there has to be the floor on crate. Because otherwise the crate would start sinking or start floating. Then for the floor, there's let's see here. I gotta make sure I get this right. Person on crate, earth on crate, floor on crate. Yep. We don't usually draw this one. It's like not as obvious because it's part of the earth. So there's the floor on the crate. And then there's like the earth below it, right? So there's the weight of the earth. There's earth on floor. The floor is not moving either. So there's crate on the floor, and then there's got to be a sub layer of the earth. And then on the earth, we'd have all the same things. Like we'd have to say, okay, there's like a bunch of these. So there's the person on the earth. There's the crate on the earth. There's the floor on the earth. And then the earth doesn't move because of us. But it's also because it has so much inertia. But there should probably be a floor on the subsurface too. Like I think there's one missing. Okay, so all that to say, the crate on the person is equal and opposite to the person on the crate. So this and this are a third law pair. Okay. This guy, it's hard to see in pink. And this guy, floor and crate and floor. This is a third law. So Newton's third law pair. So that's what you do with the third law. Now, we don't necessarily have to draw these all the time. So we know what's the crate on the person. I think that's one of the ones we need. So from the second law, we know that the crate on person has to be the force of the earth on the person. That's M person G. Floor exerts on the crate from Newton's second law. So I don't think we actually needed. So from this middle diagram, the floor on the crate has to be, let's do it this way. It's got to be the person on the crate. Yes, we do need this, plus earth on the crate. So I think it's kind of easier to answer the second one first. So this is going to be M. So person on crate is so this guy is equal to the earth on the person by Newton's third law. That's not true. No, that's by Newton's second law. So it should be the person and the mass of the crate. That's 100 kilograms of mass times 9.1 per kilogram. This one is just 65. There should be another dot O. All right. Hopefully you got a handy dandy calculator. Just to make sure this should be nice. Yeah. 181 newtons. 9.1 times 65 should be close to 650. 637.7 newtons. Okay. Well, that's good. So sometimes you're asked things in two parts, but you might have to it might be easier to think of the second part first. They really go together. They come from analyzing the multiple objects that are interacting. So, and I didn't do all the math, I didn't do all the equations, but I have my diagrams. This guy's a little messy, but the idea is that crate on person is a third law pair with person on crate. Like that's the interaction. These are the two objects interacting, are these two forces. There's also the surface, the floor, like this with the single layer of the floor, let's say. And then there's the entirety of the earth. So when you draw all four of these, the subfloor on the earth here, yeah, sublayer of the earth on the floor. That means I didn't draw one of these. There's got to be some, floor on sublayer that's part of the earth. So floor on earth. And then this earth on the floor is a gravitational pull. So there's a floor on the earth. That's the gravitational. So this arrow here, the floor on earth and earth on floor, that's a gravitational Newton's third law pair. The floor on sublayer and sublayer on floor are like a normal sort of third law. Not really. Yeah, so that's Newton's third law is if you draw these diagrams, you can find all the equal and opposite pairs. Newton's second law is you go, okay, are the forces balanced on the objects? And you use those together to argue. And then you have, do I have the numbers or not? Do I know the masses or not? So I'm going to stick around for like 10, 15 minutes to go over any questions people have. I have a couple more questions that I was planning on doing, but it's really just kind of the next question to do. And it's similar to all the stuff we just did. And so for this question, this is the part. So you need to know. It turns out after tons of experiments, we know that kinetic friction for this level, right? Like we're not talking like road tires on road level of like detail, but there's a coefficient of friction. So the friction is equal to this coefficient number times the normal force. And so experimentally, people say, okay, what are the frictional forces? If I can measure those, what are the normal forces? So you have ways of measuring that experimentally, and they create tables, and you have all these numbers. So this coefficient of friction is this number. So for kinetic means you're already moving, and static friction means you're not moving. So I'll record that part later today. And hopefully you have a chance to try it and kind of set it up, practicing what we did today.